In this problem, we are given the beam shown, and it is reinforced with 25 mm diameter bars at the bottom and 320 mm diameter bars at the top. Given the data, compressive strength of concrete, that is 34 megapascals, yielding strength of tensile and compressive reinforcements, that is 415 megapascals, and the yielding strength of shearing reinforcements, that is 275 megapascals. Lateral ties are 12 millimeters in diameter, and the base of the beam, that is 260 millimeters, we're tasked to find the following. Which of the following most nearly gives the flexural design analysis of the beam, and compute the distance of the centroid of tensile reinforcements to the neutral axis in millimeters, and calculate the nominal moment capacity of the beam in kilonewton meters. For the first problem, we need to solve for the steel ratio of the beam, that is equals to the area of the tensile reinforcement divided by base times the effective depth. Now, the area of the tensile reinforcement, usually it has the most or number of bars in the beam, so it has 5 times pi 25 millimeters squared over 4. This is the total area of tensile reinforcement divided by a base of 260 millimeters times an effective depth that we need to solve. It is the distance going from the centroid of the steel reinforcement on the tension side to the outermost edge of the compression part of the beam. So this has a value of 575 minus 60, that is equal to 515 millimeters. Solving for the C ratio, that is equals 5 times 5 25 squared over 4 all over 260 times 515, that is equal to 0.0183. And then we solve for the rho max, or the maximum C ratio, that is equals to 0.85 Fc prime beta all over Fy times 3 over 8. So plugging in the known values, we have 0.85 Fc prime, that is equals 34. And to solve for beta, that is 0.85 if the compressive strength of concrete is less than or equal to 28. However, the compressive strength of concrete is greater than 28, that is equal to 34. We need to solve for beta. So beta, that is given by the formula 0.85 minus 0.05 over 7 times Fc prime minus 28. So we have an Fc prime that is equals 34 minus 28. Solving for beta, that is equals 0.85 minus 0.05 over 7 times 34 minus 28. We get a value of 0.807. This is our beta. So solving for rho, we have Fy equals 415, then times 3 over 8. We can now solve for the maximum steel ratio. It has a value of 0.0211. This is our maximum steel ratio. And to solve for the minimum steel ratio, that is equals to 1.4 over Fy, or that is 0.25 square root of Fc prime all over Fy, whichever is greater. So we have 1.4 divided by Fy of 415, that is equal to 0.0034. And for this one, it has a value equal to 0.0035. So this one governs. Now notice that our minimum steal ratio is less than the actual steal ratio, that is equals 0.0183. So rho min, that's 0.0035, and rho actual, that is 0.0183, and it is less than the the maximum steal ratio, that is 0.0211. Which means that our analysis here for this beam should be singly reinforced beam. Knowing that we can analyze our beam as a singly reinforced beam, we can neglect the compression numbers found in this beam. Now for the second problem, to compute the distance of the centroid of tensile reinforcements to the neutral axis in millimeters, we need to compute for the value of C, given the stress strain diagram of the beam, assuming the neutral axis is found on this side here. Now since this bottom member is in tension, therefore these tensile reinforcements will experience a force of tensile force T. And for the compressive side of the beam, the concrete carries the compressive load that has a value of 0.85 FC prime AB, and the height of the compression block, that is A. If we draw its stress strain diagram, it looks somehow just like this. And the distance between the neutral axis towards the outermost compression block, that is equals C. And to solve for C, that is equals to A over beta. So we need to solve for A to solve C. And to do that, we equate T equals C. Force experienced on the tension side equals the compressive force. So for T, that is equals AS Fy, and C, that is 0.85 FC prime AB. So assuming steel yields. To solve for AS, that is the total steel area, which is equal to 5 times pi times the diameter of the bar, that is 25 millimeters squared over 4 times Fy, that is equal to 415 megapascals, equals 0.85 FC prime, that is equals 34 times A times a base of 260 millimeters. This one is a unit of Newton per millimeter squared. Solving for A, we get A equal to 135.56 millimeters. Now to solve for C, that is equals A over B, and our beta, that is equals to, which we have solved a while ago, 0.807. Solving for C, that is equals A over beta. So we have 135.56 over 0.807, which is equal to 167.98. However, we need to check if our assumption is correct. So assuming steel yields, our Fs should be greater than Fy. So let's see if our assumption is correct. So Fs equals 600 d minus C over C to check if steel would yield. So we have D, that is equal to 515, and C that we have solved right here. So we have 1239.5. So since Fy is greater than, Fs is greater than Fy, therefore our assumption that steel yield is correct. Therefore we can use this value of C in our solution. Now that we have C that is equals 167.98 millimeters, we can now solve for the problem. Now given C that is equal 167.98, to solve for this distance here, going from the centroid of the tensile reinforcement to the neutral axis, we subtract the effective depth by C. So let x be the distance from here to here. To solve for x, that is equals D minus C. So we have D that is equal to 515 minus C. Solving for x, we get a value equal to 347.02. And that serves as the final answer for the second problem. And for the last problem, to compute for the nominal moment capacity of the beam, so given this compression block right here, we can convert this into a overall resultant force that is equal to C, which is different from this C distance here. This is capital C, which represents the resultant compressive force due to this stress block, and the distance between the tensile force T and the compressive force C, that is equal to the effective depth D minus half of the height of the compression block, that is A over 2. And to compute the nominal moment, we can take summation moment along the tensile force or the compressive force. So to simplify our calculation, we can take summation moment along the direction of the compressive force. So the nominal moment is equal to D times the moment arm distance of D minus A over 2. And to solve for D, that is AS, the total steel area on the tension side, multiplied by the yield strength of steel, since our steel here would actually yield, multiplied by the moment arm distance of D minus A over 2. So we have AS that is equals 5 times pi 25 millimeters squared over 4, multiplied by Fy, that is 415 Newton per millimeter squared, multiplied by the effective depth, that is 515, minus the height of the compressive block, that is 135.56 all over 2. This is in millimeters. Now we'll solve for the nominal moment capacity of the beam. So we have 5 times pi 25 squared over 4 times 415 times 515 minus 135.56 over 2. With the value that is equals 455.52 times 10 raised to the 6 Newton millimeters. And to convert this into kilonewton meters, we multiply this by conversion factor, that is 1 kilonewton per 1000 newtons and 1 meter per 1000 millimeters. We should get the value that is equal to 455.52 kilonewton meters, since these units cancel, giving us a value that is in kilonewton meters. And this is our final answer.